Exploring the strange dead worlds that exist in our universe. Not every world in the universe is alive or active. Some planets are completely dead, no atmosphere, no volcanic activity or magnetic protection, just frozen or scorched rock drifting through space. Today, we're exploring the strange dead worlds that exist across the universe and what made them this way. The universe of dead worlds that never move again. A dead world is a planet or moon that has stopped being active inside and on its surface. It is still there, still orbiting, still solid, but it is no longer changing in any meaningful way. No active volcanoes reshaping the surface. No moving crust that rebuilds the landscape. No stable atmosphere cycling heat and gases around. No liquid water that stays on the surface for long periods. No strong magnetic field protecting it from space. When all of these systems shut down, the world becomes what scientists call a dead world. This does not mean the world disappears or breaks apart. It means the internal engine of the planet slows down until it stops doing what active planets do. Every planet starts with heat inside. That heat comes from the formation of the planet, from radioactive elements deep inside, and from pressure caused by gravity. Over time, that heat leaks out into space. Small planets lose it faster. Large planets hold on to it longer, but almost every rocky world eventually cools down enough that the inside stops moving in a strong way. Once that happens, everything above it changes too. No internal movement means no volcanoes bringing fresh material to the surface, no shifting crust to recycle old terrain, no new landforms being created. The surface becomes fixed. Whatever happened in the early history of the planet stays there. Craters from impacts remain visible for billions of years because nothing is erasing them. Old lava plains stay exactly where they solidified. Cliffs and fractures stay frozen in place. Atmosphere plays a major role in whether a world stays active or becomes dead. Some planets never had enough gravity or magnetic protection to hold onto a thick atmosphere. Others lost theirs slowly, when the solar wind stripped it away particle by particle. Without an atmosphere, there is no weather, no wind to smooth surfaces, no rain to break down rocks, no clouds to cycle heat. The surface is exposed directly to space, which means extreme temperature changes and constant radiation exposure. In some cases, a thin atmosphere might still exist, but it is too weak to support any real surface activity. It cannot move heat around in a stable way. It cannot create weather systems strong enough to reshape the ground. It is only a leftover layer, not an active system. Liquid stability is another key factor. On active worlds, liquids like water can exist on the surface for long periods, shaping valleys, carving canyons, and transporting materials. On dead worlds, liquid water is either gone, frozen underground, or unstable on the surface. If it appears, it does not last. It either freezes or evaporates quickly, depending on conditions. Without stable liquid, one of the strongest shaping forces of a planet disappears completely. Magnetic fields also matter. A strong magnetic field protects a planet from the constant flow of charged particles coming from its star. Without that shield, the solar wind slowly erodes the atmosphere over long periods of time. It also increases surface radiation, making the environment harsher and less stable. Many smaller rocky planets lose their magnetic field early because their internal heat engine shuts down. Once the core stops moving in the right way, the magnetic field fades and the planet becomes more exposed. Over time, this speeds up atmospheric loss and pushes the world closer to a dead state. When all of these conditions come together, the result is a planet or moon that no longer evolves in real time. It does not build new terrain. It does not erase old terrain. It does not cycle materials through an active system. It simply holds its shape and slowly accumulates the effects of impacts and space exposure. That is why scientists often describe dead worlds as time capsules, not because they were designed to preserve history, but because nothing active is happening to erase that history. The surface becomes a record of everything that happened long ago. Every crater is still there. Every fracture line is still visible. Every ancient flow of lava or ice remains locked in place. In many cases, you are looking at a surface that has not meaningfully changed for billions of years. This is very different from Earth. Earth is active from the inside out. Its crust moves slowly, but constantly. Volcanoes add new material. Oceans and atmosphere erase and reshape surfaces. Rain, wind, and ice break down rock and rebuild it into new forms. Even life plays a role in changing the surface chemistry. Because of all this activity, Earth constantly resets its own surface history. Most of its earlier surface is gone. Dead worlds do the opposite. They preserve everything because they are no longer resetting anything. This is why the solar system is not a collection of equally active planets. Most of its solid worlds are already in this inactive state, or very close to it. The difference between them is not appearance alone, but internal activity. Some still have heat and movement, most do not. And once that internal activity is gone, the surface becomes locked. Mercury is one example. It is small, it cooled early, and its surface has been sitting under space conditions for billions of years, with almost no change. The Moon is another. It has no atmosphere, no active geology, and no weather. Its surface is almost entirely ancient impact scars that have been preserved without interruption. Mars once had rivers and a thicker atmosphere, but as its internal heat declined and its magnetic field weakened, its atmosphere thinned and surface water disappeared. What remains is a cold desert with frozen history written into its terrain. Venus is different in temperature and pressure, but it also shows signs of long-term surface reshaping ending, where the current surface is extremely old in some regions and no longer part of a stable, Earth-like cycle. Farther out, many moons are also in this category. Some are ice-covered worlds that once had internal heating, but have now cooled to the point where their surfaces barely change. Others are rocky bodies with cratered surfaces that have remained untouched for extremely long periods of time. Even in the outer solar system, distance from the Sun does not automatically mean activity. Cold alone does not create geological movement. Internal heat is what matters, and once that fades, even distant worlds become static. What makes dead worlds scientifically important is that they show what happens when planetary systems reach the end of their internal energy. They reveal the final stage of planetary evolution for most rocky bodies. They also show that active planets like Earth are not permanent conditions. They exist inside a longer timeline where most worlds eventually slow down and stop changing from within. So when scientists study these places, they are not looking at empty objects. They are looking at worlds that have already completed most of their geological life. What remains is structure without activity, surface without renewal, and history without erasure. And that is why they matter, because they show what a planet becomes when nothing inside it is strong enough anymore to keep it alive in a geological sense. What makes a planet dead? A planet is called dead in science when it no longer has strong internal activity and no longer supports the surface systems that keep changing it over time. It is not about whether the planet exists or not, and it is not about whether it looks interesting from the outside. It is about whether the planet is still running the internal processes that keep it active, or whether those processes have slowed down so much that the planet has effectively stopped evolving in a meaningful way. To understand this properly, you have to think of a planet as something that starts its life extremely hot inside. When a planet forms, it is not a cold rock floating in space. It is a mass of material that builds up through violent collisions, pressure, and gravitational pull. All that energy gets trapped inside. For a long time after formation, the inside of a planet is like a slowly cooling engine. That internal heat is what drives almost everything a planet does on a geological level. When that heat is strong, the planet is active. When that heat fades, the planet begins to shut down piece by piece. This slow cooling is the first and most important step toward planetary death. It is not sudden. It takes billions of years. But it is steady, and once it starts, it is very difficult to reverse. Inside most rocky planets, there are elements like uranium, thorium, and potassium. These are radioactive elements that release heat as they decay. That heat is one of the main reasons a planet stays active for a long time. It keeps the inside warm enough for movement. It keeps parts of the mantle soft enough to flow slowly. It keeps pressure differences alive that push material upward and pull material downward. But radioactive decay is not endless. Over time, the amount of heat produced slowly decreases, not in a dramatic way, but in a constant reduction that never stops. As that internal heat drops, the first major system to weaken is convection inside the mantle. Convection is the slow movement of hot material rising and cooler material sinking. This movement is what drives plate tectonics on planets like Earth. When convection slows down, the crust stops moving in large pieces. The surface begins to lock into place. It does not immediately become dead, but it starts losing its ability to renew itself. Once convection becomes too weak, plate tectonics stop. This is a major turning point in a planet's life. Plate tectonics is one of the strongest recycling systems a planet can have. It takes old surface material and pushes it back into the interior, where it is melted and reformed. It also creates new surface material through volcanic activity at plate boundaries. Without this system, the surface is no longer recycled. It becomes static. At this stage, volcanic activity also begins to fade. Volcanoes are directly connected to internal heat and mantle movement. When those weaken, volcanoes become less frequent and eventually stop. Without volcanoes, the planet stops adding fresh material to its surface. No new lava plains, no new mountain chains formed by internal pressure, no resurfacing of old terrain. The surface starts aging without reset. This is the beginning of what scientists call geological shutdown, but it does not happen in one moment. It is a long process where each system weakens at a different rate. First, the deep movement slows. Then the crust becomes less active, then volcanic systems stop, and finally almost all internal reshaping ends. When this happens, the planet becomes geologically quiet, but it is not fully dead yet. It still has other systems that might be active, especially its atmosphere, if it still has one. Atmospheres are not permanent unless they are constantly maintained. A planet can lose its atmosphere slowly through several processes, and one of the most important is solar wind stripping. The solar wind is a stream of charged particles coming from a star. It is constant. It is always flowing outward. If a planet has a strong magnetic field, that field can deflect most of these particles and protect the atmosphere. But if the magnetic field is weak or has disappeared, the solar wind can directly interact with the upper atmosphere. Over long periods of time, this interaction removes particles from the atmosphere and carries them away into space. It is not a violent explosion. It is a slow leak that never stops. This is what happened on Mars. Mars once had a thicker atmosphere, and there is strong evidence that it had liquid water on its surface. But Mars is smaller than Earth, and it cooled faster. As its internal heat dropped, its magnetic field weakened and eventually disappeared. Without that protection, the solar wind began stripping away the atmosphere layer by layer. As the atmosphere became thinner, the planet lost its ability to hold heat efficiently. Temperatures became more extreme. Liquid water became unstable. Surface conditions became harsher, and once the atmosphere became too thin, it could no longer support long-term surface activity like weather or stable liquid cycles. This pushed Mars closer to a dead state. Atmospheric collapse is not only about losing air, it also changes how the surface behaves. With a thick atmosphere, a planet has weather systems that move material around, erode rocks, and reshape landscapes over time. Wind can smooth surfaces. Rain can break down rock and carry sediment. Clouds can redistribute heat. When the atmosphere weakens or disappears, all of these processes stop. The surface becomes exposed directly to space, and from that point on, change becomes extremely slow. Another major factor in planetary death is the loss of a magnetic field. A magnetic field is created by movement inside a planet's core. When the core is hot and fluid, it can generate electric currents that produce a magnetic field. But as the core cools, that movement slows down. Once the core becomes too solid or too stable, the magnetic field weakens and eventually disappears. Without a magnetic field, a planet is exposed to constant solar radiation and particle bombardment. Over time, this does two things. First, it strips away atmosphere. Second, it increases radiation levels on the surface. This makes the environment more hostile and less stable for any chemical processes that might rely on a protected surface environment. The loss of a magnetic field does not immediately kill a planet's activity, but it removes one of its strongest protective systems, making all other systems more vulnerable. When internal heat loss, atmospheric collapse, and magnetic field loss happen together, the planet moves deeper into a dead state. But there is still another level that defines planetary death, and that is the complete shutdown of surface renewal systems. On an active planet like Earth, the surface is constantly being rebuilt in multiple ways. Plate tectonics moves large sections of crust. Volcanoes bring new material from inside. Weather systems break down rock and redistribute it. Water flows carve channels and reshape land. Even ice moves and reshapes terrain over time. All of these systems work together to keep the surface young in geological terms. When a planet becomes dead, all of these systems stop working or become extremely weak. No plate movement means no large-scale reshaping. No volcanic activity means no new material added from below. No atmosphere means no weather-driven erosion or redistribution. No stable liquid means no river systems or long-term surface carving, and no internal heat means no driving force to restart any of these processes. This is what scientists mean when they talk about geological shutdown. It is not one event. It is the complete loss of all processes that actively renew a planet's surface. Once this happens, the surface becomes a long-term record of whatever happened in the planet's past. Craters remain visible because there is nothing to erase them. Old lava flows stay exactly where they cooled. Fault lines and fractures remain locked in place. Even chemical signatures from ancient environments remain preserved in rocks because there is no active system breaking them down or recycling them. At this stage, the planet is no longer building a new surface story. It is only preserving the old one. Surface sterilization also becomes important in this phase, especially from space radiation and impacts. Without an atmosphere or magnetic field, the surface is constantly exposed to high-energy particles from the star and from cosmic sources. Over time, this radiation changes the chemistry of surface materials. It breaks down complex molecules and alters rock structures at a slow but constant rate. This does not reshape the surface visually in a fast way, but it does change the chemistry of the upper layer of the ground. Impact cratering also becomes more visible over time. On active planets, craters can be erased or hidden by erosion and tectonics. On dead planets, every impact stays. Small impacts remain small scars. Large impacts remain deep basins. Over billions of years, the surface becomes a layered record of collisions, with newer craters sitting on top of older ones, all preserved without interruption. This is why dead planets often look heavily cratered and extremely old, not because they are being constantly bombarded, but because nothing is removing the evidence of those impacts once they happen. When comparing all of this to Earth, the difference becomes very clear in scientific terms. Earth is still active in all major systems. Its internal heat is still strong enough to drive mantle convection. Plate tectonics is still moving continents slowly. Volcanoes are still active in many regions. The atmosphere is thick and constantly cycling gases and heat. Oceans are still flowing and reshaping coastlines. Weather systems are constantly changing the surface. Even life contributes to surface chemistry and material cycles. Earth is still in what scientists would call a geologically active state. It is still being reshaped from the inside and the outside at the same time. Most other rocky bodies in the solar system are not in that state anymore. They are either fully dead or in the final stages of losing their remaining activity. Some still show limited internal heat or weak atmospheric remnants, but they are no longer fully active systems. This difference is not small. It is the main reason planets look so different across the solar system. It is not just distance from the Sun or size alone, it is whether the internal systems are still running or have already shut down. And once those systems shut down, the planet enters a long phase where almost nothing changes except slow exposure to space, slow accumulation of impacts, and slow chemical alteration of its surface without any active rebuilding to balance it. Mercury, The frozen metal world. For thousands of years, Mercury was little more than a moving point of light in the sky. Ancient astronomers watched it appear briefly near the horizon, before sunrise or after sunset, only to disappear again into the bright glow of the sun. Unlike planets that could be seen high in the night sky for long periods, Mercury was difficult to observe. It never wandered far from the sun from Earth's point of view, and because of that, many early civilizations struggled to study it properly. The ancient Greeks observed it, the ancient Romans observed it, civilizations in Mesopotamia tracked it, Chinese astronomers recorded its movements. Long before telescopes existed, people already knew Mercury was different. It moved quickly across the sky compared to the stars. In fact, it moves around the sun faster than any other planet in the solar system. That is why the Romans named it after Mercury, the swift messenger god. But despite being known for thousands of years, Mercury remained one of the least understood planets for most of human history. Even after telescopes were invented, astronomers still faced a major problem. Mercury stayed close to the sun. Looking directly toward the sun is difficult and dangerous. Observations had to be made during short periods near dawn or dusk. The planet often appeared blurry because sunlight scattered through Earth's atmosphere. Scientists could track its orbit and estimate its size, but the surface remained a mystery. For centuries, Mercury was little more than a distant world covered in questions. Then came the space age. As spacecraft began exploring the solar system during the 20th century, planets that had once been unreachable suddenly became destinations. Venus received visitors. Mars received visitors. The outer planets eventually received visitors. Yet Mercury remained difficult even for spacecraft. Getting to Mercury sounds simple because it is closer to the Sun than Earth, but in reality, it is one of the hardest planets to reach. Any spacecraft heading inward toward the Sun gains enormous speed because of the Sun's gravity. Slowing down enough to enter orbit around Mercury requires careful planning and enormous amounts of energy. Because of this challenge, Mercury remained unexplored longer than many other worlds. That changed in the 1970s. In 1973, NASA launched Mariner 10. The spacecraft reached Mercury in 1974 and became the first spacecraft ever to visit the planet. For the first time in human history, close-up images of Mercury began arriving back on Earth. What scientists saw immediately surprised them. Mercury looked remarkably similar to Earth's moon. The surface was covered in craters. Huge impact basins stretched across vast distances. Ancient scars covered nearly every visible region. There were no oceans, no clouds, no rivers, and no signs of modern geological activity. Instead, the world looked old, extremely old. Mariner 10 performed 3 flybys between 1974 and 1975. During those encounters, it mapped roughly 45% of Mercury's surface. That may sound like a lot, but it also meant that more than half of the planet remained unseen. Scientists had only part of the picture. Even so, Mariner 10 completely changed the way Mercury was viewed. Before the mission, some astronomers imagined a planet that might have surprising geological activity hidden beneath the glare of the sun. Instead, the images revealed a world that appeared ancient, battered, and largely inactive. One image in particular became famous. It showed an enormous impact structure later named the Caloris Basin. This giant scar stretched roughly 1,550 kilometers across. The impact that created it was so powerful that shock waves traveled through the planet and disrupted terrain on the opposite side. Imagine an asteroid hitting with such force that the entire planet felt it. That was one of the first clues that Mercury's history had been violent. Yet many mysteries remained unanswered. Scientists still did not know why Mercury was so dense. They did not fully understand its interior. They did not know whether the core was completely solid or partially molten. They could only speculate. Then something unexpected happened. After Mariner 10, Mercury was largely ignored for decades. While spacecraft visited Mars, Jupiter, Saturn, Uranus, Neptune, asteroids and comets, Mercury sat alone near the Sun, with very little new information arriving. More than 30 years passed before another mission returned. That mission was Messenger. Launched in 2004, Messenger took a complicated path through the solar system, using multiple gravity assists to gradually slow itself down. Eventually, in 2011, it became the first spacecraft ever to enter orbit around Mercury. What followed completely transformed our understanding of the planet. Scientists expected new details. What they got was an entirely new picture. Messenger mapped the whole planet. It studied the surface chemistry. It measured the magnetic field. It investigated the interior. It photographed regions that had never been seen before. The Mercury that emerged from the mission was far more complex than anyone expected. It was still a dead world, but it was a dead world with a fascinating history. One of the biggest discoveries involved Mercury's core. Mercury is a relatively small planet. Its diameter is only about 4,880 kilometers. Yet despite its small size, it contains an enormous iron core. In fact, the core makes up roughly 85% of the planet's radius. That is extraordinary. Most rocky planets have large cores, but Mercury's core dominates the planet. If you could somehow peel away the outer layers, most of what remained would be metal. This discovery helped explain why Mercury is so dense. For decades, scientists had wondered why such a small planet packed so much mass into its size. The answer was hidden inside. Mercury is essentially a giant metal-rich world with only a relatively thin, rocky outer layer. But the discoveries did not stop there. Messenger found evidence that parts of Mercury's core may still remain molten today. That surprised researchers because Mercury is considered one of the oldest and most geologically inactive worlds in the solar system. How could a planet that appears so dead still have a partially molten core? The answer lies in the unusual structure of the planet and the enormous amount of iron inside it. Even though Mercury still possesses some internal heat, that heat is not enough to drive strong geological activity at the surface. And this is where Mercury becomes one of the clearest examples of planetary death. When scientists describe a dead world, they do not necessarily mean every single part of the interior is completely cold. What matters is whether the planet still has enough energy to reshape itself on a large scale. Mercury does not. Its mantle, the layer between the crust and core, is weak compared to Earth's. The large-scale movements that drive plate tectonics on Earth do not exist there. The volcanic activity that once reshaped parts of Mercury has largely ended. The planet is no longer renewing its surface. What we see today is mostly ancient terrain. And that ancient terrain tells a story. One of the most obvious features on Mercury is its incredible number of impact craters. Some are small, some are enormous. Some overlap older craters, creating layer upon layer of impacts that stretch back billions of years. This is one of the easiest signs that Mercury is geologically dead. On Earth, craters disappear. Wind erodes them. Water fills them. Plate tectonics destroys them. Volcanoes bury them. Given enough time, many impact scars vanish completely. Mercury has no such cleanup system. If a crater forms, it tends to stay. A crater created billions of years ago can still be visible today. As a result, Mercury preserves a record of impacts stretching back to the earliest history of the solar system. The planet is essentially covered in evidence of ancient collisions, and because nothing is actively erasing that evidence, scientists can study events that happened incredibly far back in time. But Mercury's surface tells another story as well. One of Messenger's most important discoveries involved giant cliffs known as lobate scarps. These cliffs are not small. Some stretch for hundreds of kilometers. Some rise more than a kilometer above the surrounding terrain. At first glance, they might look like ordinary ridges. They are not. They are evidence that the entire planet shrank. Imagine an apple cooling after being taken out of an oven. As it cools, the outer skin wrinkles because the inside contracts. Something similar happened on Mercury. As the planet lost heat over billions of years, its interior slowly contracted. The planet became slightly smaller. That shrinking forced the crust to buckle and crack. The result was the formation of these enormous cliffs. Scientists estimate Mercury may have shrunk by several kilometers in diameter over its history. That may not sound dramatic, but for an entire planet, it is a remarkable amount of contraction. Every one of those giant scarps is a visible reminder of a world cooling down. They are evidence that Mercury's geological engine has been shutting down for billions of years. And unlike many geological clues on Earth, they remain perfectly preserved. Another thing that makes Mercury unique is its relationship with the Sun. Mercury orbits closer to the Sun than any other planet. At first glance, that might make it seem like a hot and energetic world. The reality is much stranger. Mercury has almost no atmosphere. This single fact changes everything. An atmosphere acts like a blanket. It traps heat. It moves heat from one region to another. It reduces extreme temperature swings. Earth has this protection. Venus has an even thicker version of it. Mercury has almost none. As a result, temperatures on the planet swing between extremes that are difficult to imagine. During the day, regions facing the Sun can become hot enough to melt lead. Temperatures can climb above 430 degrees Celsius. Yet when night arrives, temperatures can plunge to around minus 180 degrees Celsius. That is a temperature change of more than 600 degrees. Very few places in the solar system experience such dramatic shifts. This happens because there is no atmosphere capable of holding heat after sunset. The moment sunlight disappears, the surface begins losing energy directly into space. The heat simply escapes. This creates one of the harshest environments found anywhere among the rocky planets. Standing on Mercury would mean experiencing conditions that swing between extreme heat and extreme cold depending on location and time. The lack of atmosphere also means the surface is constantly exposed. There is little protection from incoming space debris. There is little protection from radiation. There is little protection from the solar wind. Over billions of years, this exposure has helped shape the world we see today. The solar wind is particularly important. The Sun constantly releases streams of charged particles into space. Planets with strong atmospheres and magnetic fields can resist much of this bombardment. Mercury is in a difficult position. It sits extremely close to the Sun, where the solar wind is stronger. Its atmosphere is almost non-existent. Its magnetic field exists, but it is much weaker than Earth's. As a result, Mercury endures a constant assault from solar particles. Over immense periods of time, this exposure has stripped away material and contributed to the planet's harsh environment. This is one reason Mercury's surface appears so ancient and weathered. The planet has spent billions of years sitting close to the most powerful object in the solar system while lacking many of the protective systems that larger worlds possess. And this brings us to one of the biggest questions. Why did Mercury die so early? Why is it such an ancient and inactive world compared to Earth? The answer begins with size. Size is one of the most important factors in planetary evolution. Large planets retain heat longer. Small planets lose heat faster. The reason is simple. Heat escapes through the surface. A smaller planet has less interior volume compared to its surface area. This means it loses stored heat more efficiently. Mercury is the smallest major planet in the solar system. From the beginning, it was at a disadvantage. Its internal heat reservoir was limited. Its geological engine cooled faster. Its mantle weakened sooner. Its volcanic activity faded earlier. Its ability to reshape its surface declined long before Earth experienced similar changes. In a sense, Mercury aged quickly. While Earth remained geologically active, Mercury entered old age billions of years ago. The planet did not suddenly die. It gradually cooled, contracted, and became increasingly inactive. The giant cliffs, the ancient craters, the lack of modern volcanism, and the frozen surface all point to the same story. Mercury is what happens when a rocky planet loses the race against heat loss. The proximity to the Sun also played a role. Being close to the Sun exposed Mercury to stronger solar radiation and stronger solar wind effects than planets farther away. Over enormous timescales, this contributed to atmospheric loss and surface alteration. Instead of protecting and maintaining active systems, Mercury faced conditions that pushed it toward long-term geological decline. Today, when scientists study Mercury, they are looking at one of the oldest surviving planetary surfaces in the solar system. They are looking at a world that records events from a time when planets were still forming, when impacts were more common, and when the solar system itself was much younger. Mercury is not simply a small planet near the Sun. It is a world that reveals what planetary aging looks like when it reaches an extreme. Its scars remain visible because nothing erases them. Its cliffs remain standing because nothing reshapes them. Its surface remains ancient because the systems that create new landscapes largely disappeared long ago. And every image sent back by Mariner 10 and later by Messenger revealed the same underlying reality. Mercury is still there. Its core has not gone completely cold. Its orbit remains stable. Its metal-rich interior still makes it one of the strangest planets in the solar system. But as a world, it has largely stopped becoming something new. For billions of years, it has been preserving the evidence of what it once was. The Moon, a world that stopped. The Moon is the closest dead world to Earth, and because it has always been there in our sky, it is easy to forget just how strange it really is. People often think of the Moon as familiar, almost ordinary, because it rises every night, appears in photographs, lights up dark landscapes, and has been part of human history for as long as humans have existed. Yet the more scientists studied it, the more they realized that the Moon is not simply a companion orbiting Earth. It is one of the clearest examples anywhere in the solar system of what happens when a world runs out of energy and slowly stops changing. Today, the Moon looks quiet, but that quiet surface hides a violent history stretching back billions of years. An understanding that history is one of the reasons scientists have spent decades studying every crater, every rock, and every dark patch visible from Earth. For most of human history, the Moon was little more than a distant object. People could see it clearly, but nobody knew what its surface actually looked like. Early observers looked at the dark regions visible from Earth and imagined enormous oceans. Those dark areas were eventually given names connected to seas and oceans, names that remain today, even though scientists now know they contain no water at all. The Moon seemed mysterious because it was close enough to see yet far enough away to hide almost all of its secrets. Telescopes improved our view and revealed mountains, valleys, and craters, but even then nobody truly understood what they were looking at. The surface looked battered and ancient, but there was no way to know exactly how old it was or what events had shaped it. Everything changed in the 20th century when humans finally left Earth and travelled to the Moon itself. Between 1969 and 1972, the Apollo missions transformed the Moon from a distant object into a real place. For the first time in history, humans walked across another world. The Apollo astronauts landed in different locations, explored the surface, collected rocks, deployed instruments, and brought samples back to Earth. Those missions were not only historic because people landed there. They were historic because they allowed scientists to examine the Moon directly instead of guessing from a distance. The samples returned by Apollo revealed something remarkable. Many lunar rocks were incredibly old. Some formed more than 4 billion years ago, during a period when the solar system itself was still young. This immediately made the Moon one of the most valuable scientific objects ever studied because it was preserving evidence from a time that Earth had almost completely erased. On Earth, geological activity constantly reshapes the surface. Continents move, volcanoes erupt, rain falls, rivers carve valleys, mountains rise and wear down, oceans reshape coastlines. Over immense periods of time, old surfaces disappear and new ones replace them. Earth is constantly rewriting its own history. The Moon does almost none of that. That difference is the key to understanding why the Moon is considered a world that stopped. The first thing that stands out about the Moon is its lack of atmosphere. Earth's atmosphere seems so normal that most people rarely think about what it actually does. It protects the surface from radiation. It moves heat around the planet. It creates weather. It allows clouds, storms, rainfall, and wind. All of those processes help shape Earth's surface every day. The Moon has almost none of this protection. Its atmosphere is so thin that for practical purposes it does not exist. There are no weather systems. There are no clouds drifting across the sky. There is no rain. There are no rivers flowing across the landscape. There is no wind slowly wearing down mountains over millions of years. This absence of atmosphere changes everything. Imagine a crater forming on Earth. Over time, rain would wash material into it, wind would slowly reshape its edges, plants might grow around it, rivers could cut through parts of it, tectonic activity could eventually destroy it altogether. Given enough time, the crater might disappear completely. Now imagine a crater forming on the Moon. None of those things happen. There is no rain to fill it, no wind to reshape it, no vegetation to cover it, no flowing water to erode it. The crater simply remains where it formed. This is why the lunar surface is covered with impact scars that are unbelievably old. Some of them formed billions of years ago and still remain visible today. The Moon acts almost like a storage vault for ancient impacts. Every crater is a piece of history that survived because there was nothing powerful enough to erase it. As scientists examined Apollo samples and studied lunar terrain, they began to realize that the Moon preserves a record of an era that is difficult to study anywhere else. During the early history of the solar system, collisions were far more common than they are today. Huge objects regularly slammed into planets and moons. Entire landscapes were reshaped by impacts. On Earth, much of the evidence from that chaotic period has vanished because geological activity erased it. The Moon preserved it. That alone would make the Moon scientifically important, but there is another reason researchers consider it extraordinary. The Moon is not only preserving impact history, it is preserving evidence of its own geological death. When people imagine the Moon today, they usually picture a grey, crater-covered surface that has always looked the same. In reality, the Moon was once far more active. Billions of years ago, its interior contained much more heat than it does now. That heat drove volcanic activity on a massive scale. Molten rock rose from deep inside the Moon and spread across huge regions of the surface. Those dark areas visible from Earth, the ones early observers thought were seas, are actually evidence of that ancient volcanic activity. Scientists call them maria, or lunar seas, but they are not seas at all. They are enormous plains made of basalt, a volcanic rock created when lava cooled and hardened. Long ago, giant impacts created huge basins across the lunar surface. Later, lava flooded those basins and filled them. The lava spread across vast areas before cooling into the dark plains visible today. When you look up at the Moon and notice those dark patches, you are looking at the remains of volcanic events that happened billions of years ago. The important detail is that those volcanic events are no longer happening. The Moon's volcanic activity gradually declined as the interior cooled. Over time, less heat was available to drive eruptions. The internal engine that once powered large volcanic flows weakened. Eventually, major volcanism stopped altogether. Scientists estimate that widespread volcanic activity ended roughly 1 billion years ago, meaning the Moon has spent an enormous amount of time in a largely inactive state. That timeline is important because it shows just how long the Moon has been geologically quiet. Think about what that means. For roughly 1 billion years, the Moon has not been creating vast new volcanic landscapes. It has not been rebuilding itself. It has not been resurfacing large regions the way active planets can. It has simply existed, preserving the surface it already had. This is one reason the Moon is often described as a fossil planet surface. The word fossil is usually associated with ancient life, but in this case it refers to preserved geological history. Just as a fossil can preserve details from a distant past, the Moon preserves details from an ancient solar system that no longer exists. Every major crater tells part of that story. Every basalt plain tells part of that story. Every layer of lunar rock tells part of that story. Even modern exploration continues to reveal new details. Decades after the Apollo missions ended, scientists returned to studying the Moon with advanced spacecraft equipped with technology that Apollo-era engineers could only dream about. One of the most important examples is the Lunar Reconnaissance Orbiter. Unlike the Apollo missions, which focused on specific landing sites, the Lunar Reconnaissance Orbiter has spent years mapping the Moon in extraordinary detail. It has photographed the surface at resolutions never achieved before. It has measured topography, studied temperatures, identified geological features, and created detailed maps of nearly the entire Moon. What makes this mission fascinating is that it has allowed scientists to see just how well preserved the lunar surface really is. Features that would disappear quickly on Earth remain visible on the Moon. Tiny impact scars remain untouched. Ancient terrain remains recognizable. The history of the surface is still written across the landscape. The orbiter has also revealed how incredibly complex the Moon actually is. At first glance, the lunar surface may seem repetitive, but detailed mapping shows an enormous variety of geological features created during different periods of lunar history. Massive impact basins, volcanic plains, fractured terrain, mountains, ridges, and crater fields all tell different parts of the same story. They reveal a world that was once active, then gradually slowed down, and eventually reached a state where change became extremely rare. The more scientists study the Moon, the more valuable it becomes as a record of planetary evolution. It shows what happens when a world loses much of its internal energy. It shows what happens when volcanic activity fades away. It shows what happens when a surface is left exposed without atmosphere, weather, or major geological renewal. Most importantly, it preserves those stages with remarkable clarity because almost nothing has erased the evidence. When scientists want to understand the early solar system, they often look to the Moon because the Moon remembers events that other worlds forgot. It remembers impacts that happened billions of years ago. It remembers volcanic eruptions that ended long before complex life appeared on Earth. It remembers periods of solar system history that would otherwise be extremely difficult to reconstruct. That is what makes the Moon so different from Earth. Earth is alive geologically, the Moon is not. Earth constantly updates itself. The Moon largely preserves itself. Earth hides much of its oldest history beneath newer layers. The Moon leaves that history exposed on the surface for anyone capable of reading it. And that is why this grey world hanging above us every night remains one of the most important scientific destinations in the solar system. It is not important because it is active today. It is important because it stopped. Mars, the dead world that once had rivers. Mars is one of the most studied dead worlds in the solar system, but it was not always treated that way. For a long time, people looked at it and thought it might be similar to Earth, or at least close enough to Earth that something important could exist there. It is close in size, it has seasons, it has polar ice caps, and through telescopes it showed dark and light patterns that changed over time. That alone made scientists wonder if Mars had weather, water, or even life. For centuries, it remained a planet full of speculation because no one had ever seen its surface clearly. That changed only when spacecraft finally reached it, and what they found was not a living world or even a partially active one, but a planet that looked like it had already gone through its most active stage long ago and then slowly shut down. The first real turning point came in 1965 when Mariner 4 flew past Mars and sent back the first close images in human history. Before that moment, Mars had been imagined in many different ways. Some people thought it had canals, long artificial structures that could carry water across the planet. Others thought it might have vegetation that changed colour with the seasons. Some even believed it might have advanced life. But when Mariner 4 finally sent back images, all of those ideas collapsed in a very simple way, because the pictures showed a surface that was heavily cratered, dry, and extremely old-looking. There were no signs of large channels built by intelligent life. There were no signs of forests or oceans. Instead, there was a cold, silent surface covered in impact scars, very similar in appearance to the Moon. It was a shock, not because Mars was empty, but because it already looked like a world that had stopped changing. Even though Mariner 4 only captured a small fraction of the surface, it changed the direction of Mars exploration completely. Scientists realized they were not looking at a living Earth-like planet, but at something far more ancient in appearance. Still, the question was not fully answered. One flyby was not enough to understand the entire planet, so the next major step came in 1976 with the Viking missions, which placed the first landers directly on the Martian surface. For the first time, machines were not just passing by Mars or taking pictures from orbit, but physically sitting on the ground and performing experiments. The Viking landers revealed a surface that was dry, dusty and cold, with a thin atmosphere that offered almost no protection from radiation. The sky was not blue like Earth, but a pale reddish colour caused by dust in the atmosphere. The ground was covered in fine particles that behaved differently from Earth's soil, shaped more by wind and ancient processes than by water or biological activity. The experiments conducted by Viking looked for signs of life in the soil, but the results were confusing and did not confirm anything clear. What became more certain, however, was that Mars today is not an active world in any strong sense. It is a place where surface conditions are stable but harsh, and where the processes that shape Earth-like environments are either extremely weak or absent. But even at that stage, something important was becoming clearer. Mars was not always like this. As technology improved, orbiters and rovers began to reveal something that changed the entire scientific understanding of the planet. Mars showed strong evidence that it once had flowing liquid on its surface. This was not based on imagination or speculation, but on direct geological features. Ancient river valleys stretch across parts of the planet in winding patterns that are difficult to explain without flowing water. These channels are not shallow scratches. They are carved into the landscape in ways that suggest long periods of erosion, where something once moved continuously across the surface, shaping the terrain over time. One of the most important discoveries came from studying lake beds, especially in places like Jezero crater. Jezero is not just a random depression on the surface. It has clear signs that it once held a lake. There are features that look like river deltas, where water would have carried sediment into a standing body of liquid. There are layered deposits that suggest long-term accumulation of material in still water. These structures are important because they are extremely difficult to form without stable liquid conditions. On Earth, similar structures form in lake environments where rivers meet still water and deposit sediments over time. Seeing similar structures on Mars strongly suggests that liquid water once existed there long enough to shape the landscape in stable ways. This idea becomes even stronger when you look at the minerals found on Mars. Instruments on orbiters and rovers have detected clay minerals in several regions. These minerals are especially important because they form when rock interacts with water over long periods of time. Clay does not form quickly or easily. It requires conditions where water is present and able to chemically alter rock structures. Finding clay on Mars means that not only was water present, but it was present long enough and in stable enough conditions to change the chemistry of the surface. These discoveries all point to the same conclusion. Mars was once a very different planet. It was not the cold, dry desert we see today. It had flowing water, lakes, and possibly even long-lasting bodies of liquid on its surface. That does not mean it was Earth-like in every way, but it does mean that it had active surface conditions that no longer exist. As exploration continued into the modern era, more detailed missions like Curiosity and Perseverance added even more evidence. These rovers are not just taking pictures. They are analysing rocks, drilling into the surface, studying chemical compositions, and sending back data that allows scientists to reconstruct Mars's history layer by layer. What they continue to find is consistent with the earlier discoveries. Mars has a past that includes water activity, sediment movement, and long-term surface interaction with liquid environments. But while the surface tells a story of a more active past, the current state of Mars is very different. Today, Mars is a cold desert world. Its atmosphere is extremely thin compared to Earth's, so thin that it cannot support stable liquid water on the surface for long periods. If liquid water appears today, it either freezes or evaporates quickly, depending on conditions. The temperature on Mars is generally very low, and even at its warmest, it is still far colder than most regions on Earth. Dust storms can cover large portions of the planet and last for long periods, but these storms do not reshape the surface in the same way that water or active geology would. They move dust, but they do not rebuild landscapes. The polar regions of Mars hold large amounts of ice, and there is also evidence of ice beneath the surface in various locations. This suggests that water still exists on Mars, but it is locked in solid form or hidden underground, rather than flowing freely across the surface. The planet today is shaped more by cold, wind, and long-term exposure than by active geological cycles. One of the most important scientific questions about Mars is not just what it looks like now, but when exactly it changed from a more active world into the dead or near-dead state it is in today. Scientists still do not have a single exact moment when Mars died, because planetary change does not happen suddenly. Instead, it is a gradual process that takes place over millions and billions of years. To understand this, it helps to think about what a living planet needs in a geological sense. A planet like Earth stays active because it has internal heat that drives movement inside its mantle, which supports processes like volcanism and tectonics. It also has a magnetic field that protects its atmosphere from being stripped away by the solar wind. Mars, however, is smaller than Earth, and that difference in size is extremely important. Smaller planets lose heat faster because they have more surface area relative to their internal volume. This means the heat that drives internal activity escapes more quickly into space. As Mars cooled, its internal processes slowed down. The magnetic field that once protected it weakened and eventually collapsed. Without that magnetic field, the solar wind from the Sun began to directly interact with the upper atmosphere. Over long periods of time, this interaction slowly stripped away the atmosphere, particle by particle. This was not a sudden event, but a continuous loss that changed the planet step by step. As the atmosphere became thinner, Mars lost its ability to retain heat effectively, which led to colder conditions on the surface. At the same time, liquid water became less stable, and eventually it could not remain on the surface in a long-term stable form. As the atmosphere continued to thin, surface conditions became harsher. Radiation from space reached the ground more easily. Temperatures became more extreme. Weather systems weakened. Eventually, most large-scale surface water activity stopped. Rivers dried out. Lakes disappeared. The active cycle that once shaped the planet slowed to a point where it no longer had a major impact on the landscape. Today, Mars is often described as a cold desert world, but that description only reflects its current state. Beneath that surface lies a long history of change. The river valleys, lake beds, and mineral deposits all point to a time when the planet was not frozen and dry, but active in a very different way. The surface we see now is a record of that transition, preserved because there is very little erosion or geological recycling happening today to erase it. This is what makes Mars so important in the study of dead worlds. It is not just an example of a planet that stopped being active. It is an example of a planet where scientists can still see the evidence of both states at once. The ancient active Mars and the modern inactive Mars exist together in the same landscape, layered on top of each other in rock, soil, and mineral structures. Every mission that explores Mars today is trying to answer the same central question in different ways. Not just what Mars is now, but how it changed from a world with rivers into a world without them, and how long that process took. The answer is not written in a single place, but spread across the planet in channels, craters, minerals, ice deposits, and atmospheric traces that all point back to a slow loss of internal energy and environmental stability over immense periods of time. Mars is not simply a dry planet. It is a planet that once had flowing systems and then lost the conditions that kept those systems alive. Venus, the dead world that burned itself alive. Venus is one of the most extreme examples of a dead world in the solar system. But unlike other dead worlds that became cold, quiet, and frozen over time, Venus followed a completely different path, where it became trapped in heat so intense that its surface environment turned hostile in a permanent way. At first glance, Venus looks like a planet that should be similar to Earth because it is almost the same size, almost the same mass, and made of similar rocky material. And for a long time, scientists thought it might even be Earth's twin in structure. But once spacecraft finally managed to study it closely, the reality turned out to be completely different in almost every way that matters for surface conditions and geological activity. Early observations of Venus were extremely limited because the planet is permanently covered in thick clouds that block visible light. So for centuries, astronomers could not see its surface at all, only its bright reflection in the sky. It was known as a mysterious bright object, often called the evening star or morning star depending on when it appeared. But its true nature remained hidden until space exploration made it possible to look through its cloud layer using radar and direct atmospheric probes. The first real breakthroughs came from the Soviet Venera missions, which were designed specifically to enter Venus's atmosphere and survive long enough to send back data from the surface. These missions revealed something shocking at the time, because instead of a warm Earth-like environment hidden under clouds, they found conditions that were extreme beyond expectation. The Venera spacecraft that successfully landed on Venus did not last long on the surface. But even in the short time they operated, they sent back critical information. The surface temperature was already extremely high enough to melt lead, and the atmospheric pressure was so intense that it was equivalent to being deep under Earth's oceans, far deeper than any human or machine could normally survive without heavy protection. Later missions, especially NASA's Magellan spacecraft in the 1990s, used radar mapping to look through the thick clouds and create detailed images of the surface. This allowed scientists to see the shape of Venus in detail for the first time, revealing vast volcanic plains, large impact structures, and signs of widespread geological resurfacing. The surface conditions of Venus are among the most extreme in the solar system. The temperature is high enough to melt materials that would normally be solid on Earth, including metals like lead. This is not because Venus is close to the Sun alone, but because of what is happening in its atmosphere. The pressure on the surface is crushing, roughly 90 times the pressure of Earth's atmosphere at sea level, which means that standing on Venus would feel like being deep underwater under enormous force pushing in from all sides. The atmosphere itself is mostly carbon dioxide, and it is extremely dense, trapping heat in a way that makes the entire planet act like a sealed container that cannot release energy back into space. This is where the concept of a runaway greenhouse effect becomes essential to understanding Venus. In simple terms, a greenhouse effect happens when a planet's atmosphere traps heat from the Sun. On Earth, this process is balanced in a way that keeps temperatures stable enough for liquid water to exist. On Venus, that balance was completely lost. Scientists believe that early in its history, Venus may have had liquid water on its surface and a much more moderate climate, but over time, increasing heat caused water to evaporate into the atmosphere. Water vapor is itself a powerful greenhouse gas, so as more water entered the atmosphere, more heat was trapped, which caused even more water to evaporate, creating a feedback loop that kept increasing temperatures. Eventually, this process reached a point where the atmosphere became dominated by carbon dioxide, and water vapor could no longer condense back into liquid form on the surface. Without liquid water to absorb carbon dioxide through natural chemical cycles, the gas remained in the atmosphere and built up over time. This created a thick, dense atmosphere that trapped heat far more efficiently than Earth's atmosphere ever could. Once this state was reached, the planet entered a long-term condition where heat could not escape easily, and the surface became permanently hot. Over time, the water that once may have existed on Venus likely escaped into space. High-energy sunlight broke water molecules apart in the upper atmosphere, allowing hydrogen to escape, while oxygen reacted with surface materials or was also lost. This left behind a dry planet with almost no water cycle, no oceans, and no stable liquid environment on the surface. Without water, and without a cooling mechanism, the planet became locked into its extreme greenhouse state. Even though Venus is often described as a dead world, it is important to understand what that means in this context. Unlike Mars or Mercury, Venus is not a cold, inactive planet. Instead, it is a planet where surface conditions are so extreme that normal geological and chemical processes as we understand them on Earth cannot operate in stable ways. The surface is constantly exposed to temperatures that remain high across the entire planet, with very little variation between day and night. Because the thick atmosphere distributes heat efficiently, there is no meaningful temperature drop at night because the heat is trapped so effectively that the entire planet behaves like a single, hot environment. One of the most debated topics in Venus research is whether the planet is completely geologically inactive or whether it still has some level of internal activity. For many years, scientists thought Venus might be completely dormant, with an ancient surface that had not changed for billions of years. However, more recent radar data and analysis from missions like Magellan have suggested that Venus may still have some form of volcanic activity, or at least very recent geological resurfacing. Large regions of the surface appear relatively young in geological terms, which means they may have been reshaped or covered by lava flows within the last few 100 million years. This is extremely recent on a planetary timescale. The challenge in studying Venus is that its thick clouds make direct observation of the surface extremely difficult. Unlike Mars, where rovers can explore the ground directly, or the Moon, where samples can be collected easily, Venus hides its surface under an atmosphere that blocks visible light completely. Scientists rely heavily on radar mapping to understand the terrain, which allows them to send signals that bounce off the surface and return data about elevation, texture, and structure. This method has revealed large volcanic plains that cover most of the planet, along with features that strongly suggest past volcanic activity on a massive scale. Some regions of Venus appear smoother and less cratered than others, which suggests that the surface may have been resurfaced relatively recently in geological terms. This has led to the idea that Venus might experience episodic volcanic resurfacing, where large-scale volcanic activity occasionally renews large portions of the planet's surface. If this is true, it means Venus may still have internal heat driving geological changes, even if the surface conditions are too extreme for anything like Earth-style geology to function. However, even with this possible internal activity, Venus is still considered a dead world in terms of surface habitability and stable environmental cycles. The reason is not just temperature or pressure, but the complete absence of conditions that allow long-term surface chemistry similar to Earth. There is no stable liquid water, no carbon cycle regulated by oceans, no weather system that operates in a familiar way, and no environment that allows complex chemical processes to remain stable over time. The surface is chemically hostile, with reactions occurring under extreme heat and pressure that are very different from Earth-like conditions. The thick cloud layer above Venus also plays a major role in maintaining its extreme state. These clouds are made mostly of sulfuric acid droplets, which are highly reflective and contribute to the planet's brightness in the sky. While they block sunlight from reaching the surface directly, they also trap infrared radiation coming from below, preventing heat from escaping. This creates a stable but extreme atmospheric system, where energy is continuously absorbed and retained rather than released. When scientists compare Venus to Earth, the difference is not just in temperature or atmosphere, but in the entire system of how the planet manages energy. Earth has a balanced system where heat enters and leaves in a controlled way, supported by oceans, atmosphere, and geological cycles. Venus has lost that balance completely. Once its greenhouse effect reached a certain threshold, the system locked itself into a stable but extreme state that no longer allows recovery back to Earth-like conditions. This is why Venus is often described as a planet that burned itself into a dead state. It did not become dead by cooling down like Mercury or by losing all atmosphere like Mars. Instead, it became trapped in heat so intense that the surface environment no longer supports the kinds of processes that create dynamic Earth-like geology and climate cycles. The planet is still active in some ways, possibly even volcanically, but that activity exists inside a system that is already locked into extreme conditions. For scientists studying dead worlds, Venus is important because it shows that planetary death does not always mean cold and inactive. It can also mean extreme and overheated, where a planet's atmosphere and surface conditions become so intense that normal planetary systems break down in a different direction. Venus demonstrates that a world can still be geologically complex while still being fundamentally hostile to stable surface environments. And what makes Venus especially important in the broader study of planetary systems is that it shows how fragile the balance of conditions can be. A planet similar in size and composition to Earth can end up in a completely different state, depending on how its atmosphere evolves, how its water behaves in early stages, and how heat is trapped or released over time. Venus is not just a neighbouring planet, it is an example of a parallel path that leads to a completely different kind of dead world, one defined not by silence and cold, but by permanent heat and atmospheric pressure, so extreme that the surface becomes a locked environment where normal planetary life cycles cannot operate. The icy dead worlds, outer solar system. When most people think about dead worlds, they usually imagine places like Mercury, the Moon, or Mars. They picture rocky landscapes, endless craters, dry surfaces, and worlds that clearly look ancient. But some of the strangest dead worlds in the solar system are not found near the Sun at all. They exist far beyond the asteroid belt, in regions where sunlight is weak, temperatures are incredibly low, and entire landscapes remain frozen for immense stretches of time. Out there, around the giant planets Jupiter and Saturn, are worlds that look completely different from the rocky dead planets closer to the Sun. They are covered in ice instead of stone. Their surfaces shine with frozen materials instead of dust and sand. Some of them are larger than planets once thought to be unique. Yet despite their size and complexity, many of these worlds are examples of places where change happens very slowly, where ancient landscapes remain preserved, and where enormous portions of their surfaces have existed for so long that they have become records of solar system history. The farther you travel from the Sun, the less energy reaches planetary surfaces. Temperatures drop dramatically. Water behaves differently. Instead of flowing as liquid across the ground, it freezes solid and becomes part of the landscape itself. In the outer solar system, ice is not simply frost covering rocks. Ice becomes the rock. Entire mountains, cliffs, plains, and crater walls can be built from frozen materials. This creates worlds that seem almost unreal when compared to Earth. Yet despite their differences, many of these moons tell the same story seen elsewhere in this documentary. They are worlds that were once more active than they are today. They are worlds whose surfaces preserve ancient events because so little happens to erase them. They are worlds that have become frozen records of planetary history. The first giant collection of these icy worlds exists around Jupiter. Jupiter itself is so massive that it dominates its entire region of the solar system. Orbiting around it are dozens of moons, but 4 of them stand out above all others. These are the large Galilean moons discovered by Galileo in 1610. Among them are Europa, Ganymede, and Callisto, 3 worlds that reveal very different stages of planetary evolution. At first glance, they may look similar because they are all covered largely by ice, but the more closely scientists study them, the more their differences become clear. Europa is often presented as one of the most fascinating objects in the solar system, because beneath its icy crust, there may be a global ocean of liquid water. That possibility has made Europa famous, but when you look at its surface, you are looking at a world that appears frozen and strange. Unlike heavily cratered moons, Europa's surface is covered with cracks, ridges, and long dark lines that stretch across enormous distances. The surface looks as though it has been broken apart and refrozen many times. There are relatively few large impact craters compared to older surfaces elsewhere in the solar system, which suggests that Europa's exterior has been renewed at some point in its history. Even with this unusual appearance, Europa remains a world locked beneath extreme cold. The sunlight reaching Jupiter is only a fraction of what Earth receives. Surface temperatures remain far below freezing. Any water exposed directly to the surface would freeze almost immediately. The ice shell covering Europa may be many kilometers thick, creating a barrier between the frozen surface and whatever exists beneath it. What makes Europa interesting in the context of dead worlds is that its visible surface exists in a state of deep preservation. Changes happen slowly. Conditions remain harsh. Large regions of the Moon appear frozen in place for long periods, preserving geological clues that scientists continue to study today. Then there is Ganymede, the largest moon in the entire solar system. Ganymede is so large that it is actually bigger than the planet Mercury. If it orbited the Sun directly instead of orbiting Jupiter, it would easily qualify as one of the major worlds of the solar system. Yet despite its enormous size, Ganymede often receives less attention than Europa, because its surface does not show the same possibility of a hidden ocean interacting with the exterior in obvious ways. What makes Ganymede remarkable is the contrast between different regions of its surface. Some areas are dark and heavily cratered, showing immense age. Other regions appear brighter and more complex, marked by grooves and ridges that formed long ago when the Moon was more geologically active. Scientists believe Ganymede once experienced processes that reshaped parts of its surface, but much of that activity belongs to the distant past. Today, Ganymede presents the image of a preserved world. Large portions of its terrain have remained largely unchanged for immense periods of time. The craters remain visible. Ancient structures remain intact. There is little evidence of ongoing large-scale surface renewal. Instead, Ganymede acts like a giant archive preserving different chapters of its own history. Some regions record ancient impacts. Others record periods when the interior still had enough energy to reshape the crust. Together, they create a record that has survived because so little has happened recently to erase it. If Ganymede represents a world that once changed and then slowed down, Callisto represents something even more extreme. Callisto is often considered one of the oldest looking surfaces in the solar system. When spacecraft first sent back detailed images of this moon, scientists immediately noticed one thing: it was covered in craters almost everywhere. Small craters sat inside larger craters. Newer impacts overlapped older ones. There seemed to be no region untouched by ancient collisions. This appearance tells an important story. Callisto has experienced very little geological activity for most of its existence. Unlike Earth, where active processes constantly erase impact scars, Callisto has preserved them. The surface acts almost like a photograph taken billions of years ago and then left untouched. Every crater contributes another piece of information about the violent early solar system. When scientists study Callisto, they are not looking at a world that is actively evolving today. They are looking at a world that has spent an enormous amount of time preserving evidence of ancient events. That preservation is exactly what makes it valuable. It allows researchers to investigate periods of solar system history that are difficult to study elsewhere because active worlds have erased much of their own past. The farther exploration moved into the outer solar system, the more scientists encountered worlds that seemed frozen not only physically, but also geologically. Around Saturn, another collection of remarkable moons revealed itself. Among them, Titan stands out immediately because it is unlike any other moon in the solar system. Titan is larger than Mercury and possesses a thick atmosphere. In fact, its atmosphere is denser than Earth's. At first glance, this might seem to make Titan less of a dead world than many of the icy moons around Jupiter. But Titan's reality is more complicated. The temperatures on Titan are so low that water behaves like solid rock. Instead of water shaping the landscape, other substances take over roles that water performs on Earth. Liquid methane and liquid ethane can exist on Titan's surface because of the extreme cold. Lakes, rivers and seas made from these substances have been observed by spacecraft. This immediately makes Titan seem active and dynamic. Yet despite these unusual features, Titan remains fundamentally frozen. The energy available at the surface is extremely limited. The Sun appears far dimmer than it does on Earth. Temperatures remain incredibly low. Any processes occurring there happen under conditions completely different from those on Earth. Much of Titan's landscape appears preserved over long periods. Its thick atmosphere hides many details from direct observation, but radar studies have revealed a world where change occurs very slowly compared to Earth. Titan is important because it demonstrates that a world can still possess weather-like systems and surface liquids while remaining deeply frozen and fundamentally different from active rocky planets. Its environment is dominated by cold. Its chemistry operates under conditions that seem alien compared to anything familiar on Earth. Large portions of its history remain preserved beneath layers of ice and atmospheric haze. Looking across these worlds together reveals a pattern. Europa, Ganymede, Callisto, and Titan are all different from one another. They have different sizes, different compositions, different histories, and different levels of internal activity. Yet they share something important. They preserve the past. They are worlds where ancient features survive because the forces that erase history on Earth are either weak or absent. Earth constantly changes its appearance. Mountains erode. Oceans shift coastlines. Rivers carve valleys. Tectonic plates move continents. Volcanoes create new land. These processes make Earth geologically alive, but they also destroy records of the distant past. Many icy moons do the opposite. Their surfaces often preserve ancient events because little happens to erase them. Craters remain visible for immense periods. Surface structures survive. Geological clues remain accessible long after they would have disappeared elsewhere. This is one reason scientists are so interested in these frozen worlds. They are not simply distant objects orbiting giant planets. They are records. They contain information about the conditions that existed during the formation and evolution of the solar system. Every preserved crater, every ancient ridge, every frozen plain offers evidence from a period that active worlds have often erased. What makes these icy dead worlds especially fascinating is that they challenge simple ideas about what a dead world looks like. A dead world does not always have to resemble the moon. It does not always have to be a barren, rocky landscape. Sometimes a dead world is covered in ice. Sometimes it hides beneath a thick atmosphere. Sometimes it preserves ancient geological features with extraordinary clarity because almost nothing happens to disturb them. Far beyond the warmth of the inner solar system, these moons continue orbiting their giant planets year after year, century after century, and million year after million year. Their frozen landscapes remain largely intact. Their ancient surfaces continue preserving evidence of events that happened long before Earth developed complex life. Their histories remain written into ice, impact scars, ridges, plains, and frozen crusts that have survived immense stretches of time. And that is what makes them some of the most important preserved worlds anywhere in our planetary neighbourhood. Dwarf planets, the most ignored dead worlds. When people talk about dead worlds in the solar system, the conversation almost always goes to Mars, Venus, Mercury, or the Moon. These are the famous examples. They are the worlds that appear in documentaries, science books, and space missions year after year. Yet some of the most fascinating dead worlds are not planets at all. They exist far beyond the major planets, hidden in the cold outer regions of the solar system, where sunlight is weak, temperatures are brutally low, and change happens so slowly that entire landscapes can remain largely untouched for immense stretches of time. These are the dwarf planets, and despite being some of the most scientifically valuable objects ever studied, they are often ignored compared to their larger neighbours. For most of the 20th century, Pluto was the only dwarf planet most people knew. In fact, for generations, it was not even considered a dwarf planet. It was considered the 9th planet of the solar system. Its discovery in 1930 was one of the biggest astronomical stories of the era. Astronomers had spent years searching for a possible world beyond Neptune, believing that something unseen might be influencing the orbits of known planets. At the Lowell Observatory in Arizona, a young astronomer named Clyde Tombaugh was tasked with comparing photographic plates of the night sky. The work was repetitive and demanding. Thousands of stars appeared in every image. Tiny differences had to be spotted by eye. Then, in February 1930, a moving object was identified. A new world had been found. The discovery immediately captured public attention. A planet beyond Neptune seemed mysterious and exciting. At the time, very little was known about it. Astronomers could estimate its orbit, but almost everything else remained uncertain. Pluto was so far away that even powerful telescopes could reveal very little detail. For decades, it remained a distant point of light. Scientists debated its size, composition, atmosphere, and history. The farther observations improved, the stranger Pluto became. What nobody realized at first was that Pluto was not alone. During the 1990s, improvements in telescopes and digital imaging technology led to one of the most important discoveries in modern planetary science. Astronomers began finding large numbers of icy bodies beyond Neptune. These objects occupied a vast region now known as the Kuiper Belt. Instead of Pluto being a lone planet sitting at the edge of the solar system, it turned out to be one member of a huge population of frozen worlds orbiting in darkness. This discovery completely changed how scientists viewed the outer solar system. The Kuiper Belt was not empty space. It was a vast reservoir of ancient objects left over from the formation of the solar system itself. Many of these bodies had changed very little over billions of years. Some were small, some were surprisingly large. A few approached Pluto in size. The more astronomers looked, the more they found. Eventually, discoveries became so significant that scientists were forced to rethink what the word planet actually meant. If Pluto was a planet, then many newly discovered objects might also qualify. The result was one of the most famous debates in astronomy. In 2006, Pluto was officially reclassified as a dwarf planet. The decision remains controversial among some members of the public, but scientifically it highlighted something important. Pluto was not being made less interesting. In many ways, it was becoming more interesting because it was now understood as part of an entire population of ancient worlds, rather than a lonely outlier. What makes Pluto fascinating in the context of dead worlds is that it occupies a strange middle ground between activity and preservation. At first glance, Pluto should be completely frozen and inactive. It is extraordinarily far from the Sun. Sunlight reaching Pluto is hundreds of times weaker than sunlight reaching Earth. Surface temperatures are so low that familiar substances behave in unfamiliar ways. Nitrogen freezes, methane freezes, carbon monoxide freezes. Entire landscapes are shaped by materials that would exist only as gases on Earth. When NASA's New Horizons spacecraft finally reached Pluto in 2015, scientists expected to find a relatively simple frozen object covered with ancient craters. Instead, they found a world far more complicated than expected. One of the biggest surprises was that parts of Pluto's surface appeared younger than anticipated. Some regions contained remarkably few impact craters. This suggested that at some point in its history, processes had reshaped portions of the surface. Large plains of frozen nitrogen stretched across enormous distances. Mountains rose thousands of meters above surrounding terrain. Vast patterns indicated movement of frozen materials over time. Yet despite these discoveries, Pluto still fits within the broader category of a dead world. The reason is scale. Scientists are not asking whether absolutely nothing happens on Pluto. Instead, they are asking whether the planet is actively evolving on a large geological scale today. The evidence suggests that while Pluto may retain remnants of internal activity and may have experienced cryovolcanic processes in the past, it is not continuously reshaping itself in the way Earth does. Cryovolcanism is one of the most interesting concepts connected to dwarf planets. On Earth, volcanoes erupt molten rock. In extremely cold environments like Pluto, different materials may behave in similar ways. Instead of lava, substances such as water mixed with ammonia or other compounds may rise from beneath the surface. Scientists believe some features on Pluto could represent ancient cryovolcanic structures, evidence that internal heat once allowed materials to move upward and reshape parts of the landscape. This matters because it shows that even very distant worlds were not always frozen and inactive. Like many planetary bodies, Pluto appears to have possessed more internal energy in the past than it does today. Heat from formation, radioactive decay, and other sources may have driven activity beneath the surface long ago. Over immense stretches of time, however, that energy gradually declined. The result is a world that still preserves traces of ancient activity, but no longer experiences widespread surface renewal. One of the most intriguing ideas about Pluto involves the possibility of frozen subsurface layers, and perhaps even deeper liquid regions that may have existed at various points in its history. Scientists continue studying whether internal reservoirs could have survived beneath insulating layers of ice. Even if such regions once existed, they would remain isolated beneath a surface environment dominated by extreme cold and slow geological change. The key point is that Pluto preserves evidence rather than constantly replacing it. Much of its landscape acts as a record of earlier stages of solar system history. Features that would disappear relatively quickly on Earth can survive for enormous lengths of time. Ancient impact scars remain visible. Frozen deposits remain intact. Surface structures persist because the forces capable of erasing them are weak or absent. If Pluto represents the frozen outer frontier of dwarf planets, then Ceres represents a completely different kind of dead world. Ceres was discovered in 1801 and was initially classified as a planet. Later, it became known as an asteroid. Eventually, it was reclassified again as a dwarf planet. Located within the asteroid belt between Mars and Jupiter, Ceres occupies a very different environment from Pluto. It is much closer to the Sun, yet it still exhibits many characteristics associated with ancient and largely inactive worlds. For decades, Ceres appeared unremarkable through telescopes. It was simply a bright object moving among countless smaller bodies in the asteroid belt. That changed dramatically when NASA's Dawn spacecraft entered orbit around Ceres in 2015. The images returned by Dawn revealed a world far more complex than expected. Bright deposits appeared inside certain craters. Large geological structures suggested internal processes had occurred in the past. Evidence pointed toward the presence of water ice beneath the surface. Scientists began realizing that Ceres was not merely a giant asteroid, it was a differentiated world with a history of internal evolution. Like Pluto, Ceres appears to preserve evidence of cryovolcanic activity. One of the most famous examples is a mountain known as Ahuna Mons, which many researchers interpret as a cryovolcano. Rather than erupting molten rock, such structures may have formed through the movement of icy and salty materials from below the surface. The existence of these features tells us something important about planetary death. A dead world is not necessarily a world that was always dead. Many of these objects experience periods of activity. They evolved, they changed. Internal heat moved materials, geological structures formed, then gradually, over immense periods of time, those processes weakened. Today, Ceres does not display large-scale surface reshaping comparable to Earth's tectonic activity or active volcanic systems. Instead, it preserves evidence of ancient events. Its surface acts as a record of what happened when more energy existed within the object. This idea connects Pluto and Ceres despite their enormous differences in location, size, and composition. Both worlds occupy environments where change happens slowly. Both preserve clues from earlier periods. Both show evidence that internal processes once operated more strongly than they do today. Both lack large-scale active surface renewal, and both remind scientists that the solar system contains many more dead worlds than living ones. When people imagine planetary evolution, they often focus on dynamic worlds. They think about erupting volcanoes, shifting continents, flowing rivers, and changing climates. Yet much of the solar system tells a different story. Many worlds eventually reach stages where activity declines, heat escapes, and surfaces become increasingly preserved rather than renewed. Dwarf planets are some of the clearest examples of this process because they sit at the edge between activity and inactivity. They still carry scars from ancient impacts. They still hold evidence of cryovolcanic episodes. They still preserve traces of subsurface layers that may once have been more dynamic, but they no longer undergo the kind of large-scale surface transformation that would erase those records. As a result, they function almost like archives scattered throughout the solar system. Pluto preserves information from the frozen outer regions beyond Neptune. Ceres preserves clues from the asteroid belt. Together they reveal chapters of solar system history that larger and more active worlds often hide beneath newer geological layers. That is what makes dwarf planets so important in the study of dead worlds. They are not simply leftovers orbiting in remote regions of space. They are preserved records of planetary evolution, frozen examples of what happens when geological energy slowly fades and worlds enter long periods where the past remains visible on the surface, instead of being erased by the future. Rough edge worlds, dead but still moving. One of the biggest mistakes people make when thinking about planets and moons is assuming that worlds are either alive or dead, active or inactive, changing or frozen. Reality is much messier than that. Planetary death is not a switch that flips overnight. A world does not suddenly wake up one morning and become geologically dead. Instead, it is usually a long process that unfolds over millions or even billions of years. Internal heat slowly fades. Geological systems weaken. Surface activity becomes less common. atmospheres disappear or become unstable. Eventually, a world reaches a point where major changes become rare. But there are also worlds that exist somewhere in between. They are not fully alive in the way Earth is. They are not fully dead in the way Mercury or the Moon appear to be. They occupy a rough edge between activity and decline, showing signs that the engines inside them have not completely stopped, even though much of their history points toward eventual geological aging. These worlds are important because they reveal something that many people overlook. Planetary death is a spectrum. Some worlds are extremely active. Some worlds are almost completely inactive. Others exist somewhere in the middle, preserving evidence of both conditions at the same time. They show ancient scars that suggest long periods of inactivity, yet they also display occasional bursts of change that remind scientists the story is not over. Two of the most fascinating examples are Io and Triton. At first glance, they seem completely different from each other. One is dominated by volcanic violence. The other exists in deep cold near the edge of the solar system. Yet both help scientists understand how worlds move through different stages of planetary evolution. Io is one of the strangest places in the entire solar system because it completely breaks expectations. When people imagine a moon orbiting a giant planet far from the sun, they usually imagine something frozen and quiet. Io is neither. Orbiting Jupiter, Io is the most volcanically active world known. The surface is covered with volcanoes, lava flows, volcanic plains, and giant eruptions that can send material hundreds of kilometers above the surface. In some locations, volcanic plumes rise so high that they would completely dwarf anything ever seen on Earth. The discovery of this activity shocked scientists. When the Voyager spacecraft reached Jupiter in 1979, researchers expected to see a heavily cratered moon similar to many others in the solar system. Instead, they found a world that looked almost young. Huge volcanic features covered the surface. Bright yellow, orange, red, black and white deposits created an appearance unlike any other moon. Even more surprising, scientists actually observed active eruptions. This was the first time humanity had directly seen active volcanism beyond Earth. What makes Io especially important in a discussion about planetary death is that its activity is not driven primarily by the same mechanisms that keep Earth active. Earth retains substantial internal heat from its formation and from radioactive decay inside the planet. Io receives an additional source of energy. Jupiter's enormous gravity constantly pulls on the Moon. Because Io's orbit is slightly stretched rather than perfectly circular, the strength of Jupiter's gravitational pull changes continuously as the Moon moves. This creates tidal forces that flex the interior over and over again. The effect is similar to repeatedly bending a metal wire. Bend it enough times and it heats up. On Io, that flexing occurs on a planetary scale. The interior is continuously squeezed and stretched. Friction generates enormous amounts of heat. That heat powers the Moon's volcanic activity. The result is a world that refuses to settle down. When scientists examine Io, they see a surface that is constantly being renewed. Lava covers older terrain. Volcanic deposits bury previous features. Entire regions can change appearance over relatively short periods. Craters are surprisingly rare because volcanic activity keeps resurfacing large portions of the Moon. In many ways, Io appears more geologically active than Earth, yet this does not necessarily mean Io is a permanently active world. What makes Io interesting is that its activity depends heavily on its current orbital relationship with Jupiter. The energy source driving its volcanism is not guaranteed forever. Planetary systems evolve. Orbits change over immense periods. Conditions that exist today may not exist billions of years from now. This raises an important question. If the tidal heating driving Io eventually weakens, what happens next? The answer is that Io would begin moving along the same path, followed by many other worlds. Internal activity would decline. Volcanic eruptions would become less frequent, surface renewal would slow, ancient features would begin accumulating rather than being erased. In other words, Io demonstrates that even one of the most active worlds in the solar system may still be part of the broader story of planetary aging. That idea becomes even clearer when looking at Triton. Triton is Neptune's largest moon, and it exists in one of the coldest regions of the solar system. The amount of sunlight reaching Neptune is tiny compared to what Earth receives. At that distance, the Sun appears much smaller and dimmer. Surface temperatures remain incredibly low. Almost everything about Triton suggests a world that should be completely frozen and inactive. When Voyager 2 flew past Neptune in 1989, scientists expected to see a heavily cratered moon that had remained unchanged for billions of years. Instead, Triton delivered one of the biggest surprises in planetary exploration. The surface looked relatively young. There were fewer impact craters than expected. Large regions appeared smooth. Most surprising of all, Voyager observed dark plumes rising above the surface. These were interpreted as nitrogen geysers. Suddenly, a moon that should have been entirely frozen and inactive revealed signs of ongoing geological processes. The discovery forced scientists to rethink assumptions about what frozen worlds could do. Triton was clearly not as active as Io. It was not covered in volcanoes. It was not constantly reshaping itself, yet it was not completely dead either. The geysers likely formed because sunlight warmed dark material beneath translucent layers of nitrogen ice. Pressure built up below the surface until gas eventually erupted upward. The resulting plumes carried material into the thin atmosphere before it settled back down onto the landscape. This may sound modest compared to the giant volcanic eruptions of Io, but scientifically, it was extremely important. It showed that even in one of the coldest environments in the solar system, change was still occurring. Triton occupies an unusual position in the story of planetary death because it appears to be largely frozen while still retaining pockets of activity. Most of its landscape seems ancient and stable. Large-scale surface reshaping is limited. Internal energy is far lower than what scientists see on Earth or Io. Yet the world has not reached complete geological silence. That makes Triton a valuable example of a world existing near the boundary between activity and inactivity. One of the reasons scientists are so interested in these rough-edge worlds is because they reveal how difficult it can be to define planetary death. Consider the Moon. The Moon experienced volcanism in the distant past, but major volcanic activity ended long ago. Large-scale surface renewal is essentially absent. Most scientists comfortably describe it as a dead world. Now consider Triton. Activity exists, but it is limited. Surface changes occur, but not on a global scale. Geological energy remains present, but only in specific forms. Is Triton dead? Is it alive? The answer depends partly on how those terms are defined. The same issue appears with Io from the opposite direction. Io is clearly active today, but its activity relies on specific conditions that may not last forever. If scientists observed Io at a different point in solar system history, they might see a very different world. This is why planetary death is better understood as a spectrum rather than a category. At one extreme are worlds like Earth, where multiple geological systems operate simultaneously. At the other extreme are worlds like Mercury, where major activity largely ended billions of years ago. Between those extremes are worlds occupying transitional stages. Some retain internal heat, but show limited surface activity. Some remain frozen, yet occasionally erupt. Some preserve ancient terrain while still experiencing localized change. Some appear inactive until new observations reveal subtle signs of motion. The more scientists explore the solar system, the more common these in-between cases appear to be. This matters because it changes how planetary evolution is understood. Instead of seeing worlds as active or inactive, scientists increasingly view them as moving through long-term life cycles. Internal heat gradually decreases. Geological systems weaken. Surface renewal slows. Different worlds progress through these stages at different rates depending on their size, composition, location, and history. A small rocky world may cool relatively quickly. A larger world may remain active longer. A moon influenced by tidal heating may stay active despite its size. A frozen moon may preserve enough energy for occasional eruptions even after billions of years. Every world follows its own path. Io and Triton reveal two very different points along that path. Io shows what can happen when an external source of energy keeps a world active long after scientists might expect it to cool. Triton shows what happens when activity becomes rare but does not disappear completely. Together, they challenge the idea that planetary death is simple. The solar system is filled with worlds that refuse to fit neatly into categories. Some are clearly active, some are clearly dead. Others occupy the rough edges between those states, preserving evidence of ancient activity while still showing occasional signs of movement. And those rough-edge worlds may be some of the most valuable places scientists can study because they capture planetary evolution in progress. They allow researchers to observe worlds that have not completely stopped, yet are no longer fully active either. They reveal the long transition between geological life and geological death, a transition that can last for billions of years and leave behind landscapes that tell the story of both states at once. Exoplanet dead worlds. Billions of distant remnants. For most of human history, every discussion about planets was limited to our own solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune were the only known examples of planetary worlds. Scientists could compare them, study them, and build theories around them. But there was always one major limitation. The sample size was incredibly small. If humanity wanted to understand how planets form, evolve, age, and eventually die, 8 major planets were not enough. The solar system could not answer every question by itself. That changed during one of the biggest scientific revolutions in modern astronomy. Today we know that planets are not rare, they are everywhere. Our galaxy alone likely contains hundreds of billions of planets. Many stars appear to have planetary systems of their own. Some systems contain giant planets larger than Jupiter. Others contain rocky worlds similar in size to Earth. Some planets orbit close to their stars. Others orbit at enormous distances. Some worlds are incredibly hot. Others exist in deep cold. The universe turned out to be far stranger and far more crowded than scientists imagined only a few decades ago. What became even more surprising was that many of these newly discovered planets appeared to be examples of planetary destruction, planetary aging, or planetary environments so extreme that they fit naturally into the category of dead worlds. Unlike the dead worlds of our solar system, these planets exist so far away that spacecraft cannot visit them. We cannot land on them. We cannot drive rovers across their surfaces. We cannot directly collect rocks and bring them home for study. Everything scientists know about them must be extracted from tiny pieces of light arriving from distant stars. That challenge alone makes the discovery of exoplanets one of the greatest achievements in scientific history. For centuries, astronomers suspected that planets probably existed around other stars, but suspicion is not evidence. Stars are incredibly bright, while planets are comparatively dim. Trying to directly see an exoplanet is often like trying to spot a tiny speck beside a giant searchlight from enormous distances. The breakthrough came through indirect detection methods. Instead of looking directly at planets, astronomers began looking for the effects planets have on their stars. One of the most successful techniques became known as the transit method. The idea is surprisingly simple. If a planet passes between its star and Earth, the planet blocks a tiny fraction of the star's light. The star becomes slightly dimmer for a short period. Then the brightness returns to normal. The change is incredibly small. In many cases, the difference is less than 1%. Yet with sensitive enough instruments, astronomers can measure these tiny dips in brightness and use them to identify planets that cannot be seen directly. This method transformed planetary science. And no mission played a bigger role in that transformation than NASA's Kepler Space Telescope. When Kepler launched in 2009, its goal was straightforward but ambitious. It would stare at a huge region of space continuously, monitoring the brightness of more than 100,000 stars. Instead of looking for one planet at a time, it would search for thousands simultaneously. The results changed astronomy forever. Planet after planet began appearing in the data, then dozens, then hundreds, then thousands. Suddenly, the universe became filled with worlds. Some were unlike anything in our solar system. Others appeared vaguely familiar. Many seemed completely hostile to life, and a surprisingly large number appeared to fit the profile of dead worlds. One of the most fascinating discoveries involved planets orbiting extremely close to their stars. In our solar system, Mercury is the closest planet to the Sun. Many exoplanets orbit much closer to their stars than Mercury does. Some complete an entire orbit in only a few days. Others complete an orbit in less than a single Earth day. At such distances, the environment becomes almost unimaginable. These planets absorb enormous amounts of stellar radiation. Temperatures soar to extraordinary levels. In some cases, the surface becomes hot enough to melt rock. Scientists refer to some of these worlds as lava planets. The name is not an exaggeration. On these planets, entire regions may be covered by oceans of molten rock. Imagine standing on a world where stone behaves like water. Imagine mountains slowly melting beneath relentless heat. Imagine a horizon glowing with rivers and lakes made not of liquid water, but of liquid rock. That is the reality scientists believe exists on some lava worlds. Many of these planets are also tidally locked. This means one side permanently faces the star, while the other side permanently faces away. The same hemisphere experiences endless daylight. The opposite hemisphere experiences endless darkness. There is no sunrise. There is no sunset. One side is trapped beneath constant stellar bombardment. The other side remains locked in permanent night. The difference in temperature between these regions can become extreme. The star-facing side may reach temperatures capable of melting rock, while the night side remains dramatically cooler. These worlds are important because they reveal one possible endpoint of planetary evolution. A rocky planet that forms too close to its star may eventually lose any atmosphere it once possessed. Intense radiation can strip atmospheric gases away over time. Without atmospheric protection, the surface becomes increasingly exposed. The result is a world that remains physically present, but has lost many of the conditions necessary for long-term geological and chemical complexity. In many ways, these planets represent dead worlds created by heat rather than cold. Then there are the barren, tidally locked planets. Not every tidally locked world is a lava planet. Some orbit cooler stars. Others occupy different environmental conditions, yet many still face similar challenges. Because one side permanently faces the star, weather systems can become extreme. Atmospheres may struggle to remain stable depending on the planet's size and distance. Some worlds may experience atmospheric collapse. Others may gradually lose large portions of their atmospheres through interactions with stellar radiation. What makes these planets especially interesting is how common they appear to be. Many stars in our galaxy are smaller and cooler than the Sun. Planets orbiting close enough to receive useful amounts of energy often become tidally locked. As astronomers continue studying these systems, they increasingly encounter worlds that appear trapped in long-term environmental extremes. Some may retain atmospheres, others may not. Some may preserve active geological processes. Others may have lost them long ago. What remains consistent is that many of these planets appear far less dynamic than Earth. They look less like living planetary systems and more like environments locked into harsh equilibrium states. The farther scientists push exoplanet research, the more examples they find suggesting that planetary death may be common throughout the galaxy. Another remarkable category involves strip-core planets. These worlds may represent some of the most dramatic examples of planetary transformation ever discovered. To understand them, imagine a giant gas planet similar to Jupiter. When such a planet forms, it accumulates enormous quantities of hydrogen and helium. These gases create a thick outer envelope surrounding a denser core. Now imagine placing that planet extremely close to its star. Over time, powerful stellar radiation begins attacking the atmosphere. Particles stream away into space. Heat causes the atmosphere to expand. The outer layers become increasingly vulnerable. Millions of years pass, then billions. Gradually, the atmosphere disappears. The giant planet begins losing the very material that once defined it. What remains may be a dense core that was once hidden beneath enormous layers of gas. Scientists believe some observed exoplanets could be exactly this type of object. They may be the exposed remnants of former gas giants. In other words, these planets are not simply dead worlds. They may be planetary skeletons, the surviving cores of worlds that were once dramatically larger. This possibility is one of the most fascinating ideas in modern astronomy because it shows how violent planetary evolution can be. A planet's current appearance does not necessarily reveal its original form. Some of the rocky worlds observed today may have started their lives as giant gas-covered planets. Billions of years of atmospheric loss transformed them into something entirely different. The more astronomers study distant planetary systems, the more they realize that atmospheric loss may be one of the most important processes shaping planetary death. Atmospheres are not permanent. They can be stripped away by radiation. They can be removed by stellar winds. They can be lost through internal changes. They can gradually leak into space over immense periods. Once an atmosphere disappears, everything changes. Surface temperatures become less stable. Protection from radiation decreases. Chemical cycles weaken or disappear. Water becomes harder to maintain. The environment becomes increasingly hostile. This process appears again and again throughout planetary science. It happened on Mars. It likely affected countless exoplanets. It may be one of the most common pathways toward planetary decline. One reason scientists find exoplanet dead worlds so important is that they expand the concept far beyond our solar system. When people study Mercury, Mars, or the Moon, they are examining a handful of examples. Exoplanets provide access to thousands. Each new discovery adds another data point. Each system reveals another variation of planetary evolution. Some planets die from heat. Some die from atmospheric loss. Some may die from tidal locking. Some may lose their oceans. Some may lose their atmospheres entirely. Some may be stripped down to their cores. Others may spend billions of years trapped beneath relentless radiation from their stars. The remarkable thing is that astronomers are only beginning to understand how many of these worlds exist. Every improvement in telescope technology expands the search. Every new mission reveals additional planets. Every new dataset uncovers environments that challenge previous assumptions. What was once a scientific question has become a scientific reality. The galaxy is filled with planets, and among those planets, enormous numbers appear to be worlds that have already passed through their most active stages, lost crucial parts of their environments, or become trapped in conditions so extreme that long-term planetary vitality is no longer possible. Some are frozen remnants, some are scorched remnants, some are exposed cores left behind after planetary transformation. Some are barren worlds locked forever to their stars. Together they suggest something profound about planetary evolution across the universe. Dead worlds are not rare exceptions. They may be one of the most common outcomes of planetary history. Planetary stripping, how worlds die. When scientists study planets across the solar system and beyond, one pattern appears again and again, and it is that worlds do not stay the same forever, because every planet is constantly exposed to forces that slowly reshape it, weaken it, or completely remove the conditions that once made it active. This long process is often called planetary stripping, and it is not one single event, but a collection of different mechanisms that work over huge periods of time, sometimes acting together and sometimes acting separately, but always pushing planets toward change, and in many cases, toward a state that can be described as a dead world. One of the most important forces in planetary stripping is stellar radiation erosion, which is the steady pressure that comes from a star constantly releasing energy into space, because every star produces light, heat, and charged particles that spread outward in all directions, and any planet that orbits that star must exist inside this environment, whether it is close or far, protected or exposed, stable or unstable. For a planet with a strong atmosphere and magnetic field, this radiation can be managed for a long time, but for many worlds it becomes a slow and continuous process of damage. High-energy particles strike the upper atmosphere, knocking molecules loose, heating them, and in some cases giving them enough energy to escape the planet's gravity entirely. And when this happens repeatedly over millions or billions of years, the atmosphere begins to thin in a way that is almost invisible in the short term, but extremely important in the long term. This process is not dramatic like an explosion or sudden collapse, because nothing about it happens in a single moment. Instead, it is more like a constant erosion that never stops, where each second a tiny amount of atmospheric material is lost, and over long periods that loss becomes significant enough to change the entire nature of the planet. Mars is one of the clearest examples of this kind of atmospheric loss, because evidence from spacecraft shows that it once had a much thicker atmosphere capable of supporting rivers, lakes, and long-lasting surface water. But today, that atmosphere is extremely thin and unable to maintain liquid water on the surface for long periods. Scientists believe that the loss of Mars's magnetic field played a major role in this process because without a strong magnetic shield, the solar wind was able to interact directly with the upper atmosphere, stripping it away gradually and reducing the planet's ability to retain heat and moisture. Atmospheric removal is one of the most important turning points in planetary evolution, because once a planet loses enough of its atmosphere, many other systems begin to fail at the same time. Since temperature regulation becomes weaker, radiation reaches the surface more easily, and liquid water becomes unstable or completely impossible in long-term conditions. And this combination pushes the planet closer to a state where surface activity slows down and geological processes become less dynamic. Over time, the planet does not just lose air, it loses part of the system that keeps its surface active and changing. Another major mechanism of planetary stripping is impact destruction, which comes from the early history of planetary systems when space was filled with large numbers of rocky and icy bodies moving at high speeds. And during this early period, collisions were extremely common, often shaping entire planetary surfaces through repeated impacts. In the early solar system, planets did not exist in a stable environment like today, but instead they formed in a chaotic region filled with debris, where objects collided constantly, sometimes merging to form larger bodies and sometimes breaking apart into smaller fragments. And in some cases, these collisions were so powerful that they permanently altered the evolution of entire worlds. Large impacts can strip away parts of a planet's atmosphere, melt large portions of its surface, or even eject material into space. And when this happens repeatedly over time, the surface of a planet becomes heavily scarred with craters that preserve the memory of these violent events. The Moon is one of the best examples of this process because its surface is covered with impact craters that have remained largely unchanged for billions of years, since there is almost no erosion or geological activity to erase them. Mercury also shows a heavily cratered surface, revealing a long history of early bombardment that shaped its appearance and influenced its evolution. In extreme cases, large impacts can completely change the structure of a planet, such as the leading theory that a giant impact between early Earth and another large object led to the formation of the Moon, which shows that impacts are not just destructive, but can also create entirely new systems, although in most cases their effect is to strip away or damage existing planetary conditions. Over time, as the number of large impacts decreased in the solar system, their role shifted from reshaping planets to simply preserving evidence of early conditions. Another major process involved in planetary stripping is internal cooling, which refers to the gradual loss of heat from inside a planet over long periods of time, because all rocky planets begin their existence with significant internal energy, some from the heat of formation when material collided and compressed during planetary growth, and some from radioactive decay of elements within the planet's interior. And this internal heat is extremely important because it drives geological activity such as volcanism, tectonics, and mantle movement. While a planet is still hot inside, its surface can remain active, with volcanic eruptions resurfacing areas and internal movement creating changes in the crust. But as time passes, this heat slowly escapes into space, and the internal engine that drives geological activity begins to weaken. Smaller planets cool faster because they have a higher surface area relative to their volume, which allows heat to escape more efficiently. And this is one reason why Mercury and the Moon became geologically inactive earlier than Earth, because their smaller size meant they could not retain internal heat for as long. As internal energy decreases, geological activity slows down, Volcanic eruptions become less frequent, tectonic movement weakens or stops entirely, and the surface begins to preserve older features rather than constantly renewing itself. Mars shows evidence of this kind of decline, where ancient volcanic regions and dried river systems suggest a more active past, while the present surface shows limited geological activity compared to Earth. Over billions of years, this cooling process contributes to the transition from active planet to dead world, where the surface becomes increasingly static and unchanging. The fourth major mechanism of planetary stripping is orbital disruption, which refers to changes in a planet's orbit that alter its environment in ways that can affect temperature, radiation exposure, and long-term stability. A planet's orbit is one of the most important factors in determining its surface conditions, because even a small change in distance from a star can significantly alter the amount of energy the planet receives, and over long periods this can influence whether liquid water can exist, whether atmospheres remain stable, and whether geological activity continues in a balanced way. In some planetary systems, gravitational interactions between large planets can cause smaller planets to shift their orbits over time, sometimes moving closer to their star and experiencing increased heating and atmospheric loss, or moving farther away and entering colder regions where surface liquids freeze and geological activity slows. In extreme cases, orbital changes can destabilize entire planetary systems, leading to collisions, ejections, or permanent changes in environmental conditions. Many exoplanet systems observed by astronomers show evidence of planets in very close orbits around their stars, far closer than Mercury is to the Sun, and in these environments radiation levels are extremely high, leading to conditions where atmospheres may be stripped away or surfaces become extremely hot and unstable. This shows that orbital position is not fixed in its effects, but deeply connected to planetary survival and long-term evolution. When these four mechanisms are viewed together, stellar radiation erosion, impact destruction, internal cooling, and orbital disruption, they form a complete picture of how planets change over time and how many of them eventually move toward states that can be described as dead worlds, where geological activity slows, atmospheres weaken or disappear, and surface conditions become increasingly static. The future fate of Earth-like worlds can also be understood through these same processes, but in a long-term scientific projection based on current knowledge of solar evolution and planetary physics. The Sun is not a static object, but a star that slowly changes over time, gradually increasing in brightness as it converts hydrogen into helium in its core. And this slow increase in energy output will eventually have a major effect on Earth's climate and surface conditions over billions of years. As solar output increases, Earth will receive more heat, which will slowly affect the planet's temperature balance, leading to gradual warming over extremely long timescales. This warming will not be immediate in human terms, but over geological time, it will become significant enough to change ocean behavior and atmospheric conditions. One of the key predictions in this long-term model is that Earth's oceans will eventually begin to evaporate more rapidly as global temperatures rise, increasing water vapor in the atmosphere, which is itself a powerful greenhouse gas. And this creates a feedback process that increases heat retention even further. Over very long periods, this process may lead to a point where surface water becomes unstable or disappears entirely, and the planet gradually moves toward a much hotter and more hostile state. Eventually, if solar evolution continues as expected, Earth's surface conditions may become too extreme for current forms of life, and the planet would transition into a state more similar to other hot and inactive worlds, where stable liquid water no longer exists and surface environments become permanently altered. This future projection is often compared with Mars and Venus because both of those planets already show different stages of this kind of planetary evolution. Mars appears to have gone through atmospheric loss and surface drying, moving from a more active past into its current cold and dry state. Venus appears to have undergone a runaway greenhouse effect, where heat became trapped in its atmosphere, leading to extremely high surface temperatures and a complete transformation of its surface environment. Both planets show different outcomes of planetary stripping processes acting over long periods of time, even though their paths were very different. When all of this is considered together, from solar system planets to distant exoplanets, a larger pattern begins to emerge in planetary science, and it is that most planets in the universe are not in highly active states like Earth, but instead exist in conditions where some combination of atmospheric loss, internal cooling, impact history, or orbital changes has already altered or reduced their activity. In this view, dead worlds are not rare exceptions, but extremely common outcomes in planetary evolution, because active geological systems depend on a balance of conditions that does not last forever, and over long enough periods that balance is gradually lost as internal energy fades, atmospheres escape, or environmental conditions change. Future space telescopes such as the James Webb Space Telescope and next-generation observatories are now being used to study these processes directly in exoplanet systems, with the goal of detecting atmospheric loss in real time, observing how planetary atmospheres change under stellar radiation, and identifying planets that are currently transitioning between active and inactive states. These observations are important because they allow scientists to move beyond static snapshots of planets and instead study planetary evolution as an ongoing process occurring across the galaxy. As technology improves, scientists expect to find more examples of planets undergoing stripping processes, where atmospheres are being eroded, surfaces are being exposed, or internal activity is slowing down. And each of these discoveries adds more detail to the understanding of how common planetary death is across the universe, and how many worlds may eventually pass through similar stages of decline over cosmic time.